Hello everybody.
Hi everyone. By the end of this video, you should be able to know and do everything with inverse functions. So first, what is an inverse function? And for the big reveal, my precise mathematical definition is inverse functions are functions that undo each other. So what does this mean? I'm going to go back to a basic illustration you probably saw back in the day when you started to learn about numbers, and that's a function machine. So something goes in, you do something to it, and then something comes out. So if I put 5 in and I add 3, my output is 8. And if I subtract 3, my output is 5. So I wind up with the same thing I started with. That's because plus 3 and minus 3 are inverse functions. So I do something and then I undo it. Or if I go backwards, I start in 5, I might subtract 3, I get 2, then I add 3, I get 5. So either way you go, you're going to get the same thing from start to finish, and that's because you're doing inverse operations or operations that undo each other. Okay, so we're going to test inverse functions in a couple different ways here. So first, what I want us to do is go back to chapter 1, and I want us to compose f of x with g of x. So remember, the composition of functions means you take one function, plug it into another. So this one means f of g of x. This one means g of f of x. Two different ways to write it. So I'm going to pause the video. I want you to do both of these things on your note sheet, and I will come back with the answer. Okay, so I've completed both compositions. You can check through my work here. But when I plug in g of x to f, it looks like this, and everything winds up canceling and I get x. Or when I plug in f of x to g, again, everything winds up canceling and I get x. Look through my work if you need to. Okay, so the reason that this happens is because 2x minus 4 and x plus 4 over 2 are what we call inverse functions, which means they undo each other. And if you think back to our basic illustration up here, if you undo all the operations, you're going to be left with just the input. And what is the input of 2x minus 4 and x plus 4 over 2? Well, the input is just x. So if I compose the two inverse functions, everything's going to undo each other, so you'll just be left with the input, which is x. So my conclusion is, if you compose or do function composition, whatever you want to call it, I'm just going to write compose. If you compose two inverse functions, we'll abbreviate that to fun because functions are fun, okay, then the output should always be x. And that should work going both ways, like it did up there. Both of the outputs are x. Again, the reason this is because inverse functions undo each other. So all the operations have their inverse operation. So I'm going to divide by 2 and multiply by 2. I'm going to add 4 and I'm going to subtract 4. Okay, that's a good thing to look at if you're trying to figure out if these two functions are inverse functions. Okay, so the reason I need to know this is because this is one way to check are two equations inverse functions, or are two functions inverse functions. Okay, in order to check that, if you compose them both ways, so I plug f into g and g into f, then the output is x. If the output is x for both of them, then they're inverse functions. So again, this is a method to check for inverses, or inverse functions. Again, abbreviating with fun, because functions are fun, right? Okay, we're going to look at another example. We're going to use the same two functions. So f of x is still 2x minus 4. G of x is x plus 4 divided by 2. And I want us to come up with a table. So again, I'm going to pause the video, and I want you to fill out the output column for these inputs. Go. Okay, so once that's done, you get these two tables here. And the question is, what do you notice? Well, the first thing I notice is I've already proven that these two things are inverse functions by composing them and realizing that the output is x, so they undid each other. So I know these are inverse functions. And if I look at the table, what you should be noticing is a pattern here. The inputs of f of x are the outputs of g of x. And the outputs of f of x are the inputs of g of x. Okay, so really what winds up happening is if I have the point 2, -8 on f of x, then I know on g of x I should have the point -8, -2. So the inputs and outputs have switched. If I have 2, 0, I should have 0, 2. So conclusion, inverse functions, or for inverse functions, for inverse functions, the inputs and outputs always switch. Okay, so my x's become my y's become my x's. If you need to write that down, go ahead. Okay, now I'm going to graph these tables and see what I notice. So go ahead and do that on your own. You already have the table, just plot the points. Okay, so I've graphed both functions. I'm not going to talk about this in this video because it's easier to see with some patty paper. But you can start thinking, what do you notice? And we will continue to talk about this in class. Remind me if I forget. Okay, last example of how to find an inverse function, and a little notation here as well. So if f of x is our function, we call an inverse function f to the negative first of x. Okay, this is no longer an exponent, this is notation. So this notation is a universal notation, meaning inverse. Okay, not f to the negative first power, it means f inverse of x. Okay, so if I want to find an inverse function, I want to go back to that graph idea. So what we learned when we made that table is that for inverse functions, the inputs and the outputs switch. So if you want to find an inverse function, that's exactly what you're going to do, is you're going to switch the inputs and the outputs. So remember, your input to a function is x, your output is f of x. Now sometimes for the solving purposes, it's easier to think about the f of x as y, because remember they're the same thing, but two different notations. So this is function, this is equation. I'm going to change this to x to make it a little bit easier to solve. Okay, now to find the inverse function, all you have to do is switch the inputs and the outputs. So I'm going to essentially be switching my x and my y. So x equals 3y plus 5 would be the inverse function of f of x. Now this is not proper function notation, obviously. You want to isolate the output, or you want to isolate y, and then you'll get the actual function. So if I do that, I'm going to subtract 5. So you get x minus 5 equals 3y. And then to get y alone, you have to divide by 3. So your final inverse is y equals, I'm just switching the order here, x minus 5 over 3. Now it was f inverse of x, so I'm going to go back and rewrite this in inverse function notation. So you get f inverse of x equals x minus 5 over 3. And there's a good way to kind of just double check this, especially with a basic example. In this problem, you had addition by 5 and multiplication by 3. In this one, you have subtraction of 5 and division by 3. So addition and subtraction undo each other, so they're inverse functions. Multiplication and division undo each other, so they're also inverse functions. So that's a quick way to kind of check and make sure you got the right inverse. Okay, so the conclusion of this one, and I didn't put a place for a conclusion, but you can write it in, is that to find inverse functions, or to find inverses, to simplify it, and this is very not precise, but this is a good way to remember it. Essentially, you're just switching the x's and the y's. Okay, now what I've just written here is the how. You need to think about what inverse functions mean to understand the why. And the why is almost more important than the how. Okay, so if you have any questions about the why, please ask them. Otherwise, I hope you learn lots about inverse functions, and we will continue to work in class. Have a good night.